Have you ever wondered how your airline is able to route you to your favorite destination at a minimum cost and with the fewest number of stops? Today's algorithm answers a practical question. What's the cheapest way to fly from some source to some destination, all in at most K stops? In today's problem, we'll dive into an efficient solution that also covers an application of the famous Dijkstra's algorithm, min heaps, and memoization. Let's get started. So what even is Dijkstra's algorithm, and why might it be helpful to answering this question? Dijkstra's algorithm is a graph search algorithm primarily used to find the shortest path between nodes in a weighted graph. This algorithm is classified as a single-source shortest path algorithm, as it finds the shortest path from a single-source node to all other nodes in the graph. This technique can be thought of as greedy. And as we know from previous videos on this channel, a greedy algorithm chooses a locally optimal choice at each step of the overall calculation. Dijkstra's algorithm is particularly useful for solving problems such as route planning in transportation networks, network routing protocols, and optimizations in various logistical and supply chain systems. With the idea of Dijkstra's algorithm in mind, our plan is to modify Dijkstra's algorithm so that it only calculates up to K stops. Starting at our source node, we will iterate through each vertex from that node and choose the locally optimal choice. We will continue updating until either we have arrived at our destination or we have run out of either K stops or nodes in general. We will get help implementing this idea with two important data structures: a priority queue, which can also be thought of as a min heap in this case, and a hash map for memoization. A priority queue is like a queue except that instead of processing elements only as first in, first out, they are also processed in terms of their priority. In this case, the priority queue prioritizes nodes in order of minimum cost. Let's also consider what we mean by memoization. Memoization is caching or saving the results of a previous calculation so that it may be used quickly in a future calculation that requires it. We can use a hash map to store the results of previous sub-branch calculations that may be used as we traverse through the weighted graph. Looking up these sub-calculations is done in constant time, greatly reducing the time complexity of the algorithm compared with if we needed to recalculate the sub-calculations in each iteration. With all of these considerations in mind, we are finally ready to dive into our code. First, we initialize a dictionary of lists, and for each tuple in our list of flights, we will create an adjacency map that maps a source to a destination and its associated cost. The next step will be to initialize a priority queue with the tuple 0, source, -1, representing our starting position at 0. We now arrive at the main event. While there are still elements in the priority queue, we pop the minimum value tuple from our queue, maintaining the min heap structure. If the city that we had popped was our destination, we are done and can return the cost we have accumulated so far. If not, we need to check that the number of stops we have traveled to is less than K. This guard ensures that the algorithm won't find an optimal solution using more than K stops. Then, we use the city to check in our default dict. If the information of the city hasn't yet been stored, or the current cost plus price is less than the memoized value, we will either create a new memo value or update the memo value to reflect the current cheapest way to travel to a neighbor. We will finally push the updated cost, neighbor, and number of stops on the heap so that the heap remains in minimum order. What is the time and space complexity of this algorithm? The time complexity for the given code can be expressed as O of n times m times e log e, where n is the number of cities, m is the number of flights, e is the maximum number of stops. This complexity arises from the use of a priority queue, or heap queue, to perform the Dijkstra's algorithm on the graph defined by the flights. The heap queue operations involved O of log e, time complexity, and the entire algorithm runs until the priority queue is empty, resulting in the mentioned overall time complexity. The space complexity of the code is primarily dependent on the graph's storage and the priority queue. Since the graph is stored using a default dict, the space complexity for the graph can be considered as O of m, where m is the number of flights. Additionally, the priority queue, or PQ, also contributes to the space complexity. Therefore, the space complexity can be considered as O of m plus n. Now that's a problem. Come back soon and maybe we'll cure cancer or something.